All right, Math 30-2. Welcome back to another edition of Math from Home. Hopefully, we only got like a couple more episodes left in us, and then we're back in person. That'd be nice, wouldn't it? Yesterday, we watched a video and we learned about fundamental counting principle. Let's do a quick review question. So, example 10a, how many ways can the letters from the word prime be arranged? So to figure out how many ways you could arrange those letters, you're going to realize there's 5 letters. I'm going to use the fundamental counting principle. So it means you're going to put 5 empty slots, and you're going to say how many numbers could go in the first spot, or how many different letters could go in that first spot. Well, there's a P, R, I, M, or E. Any of those 5 letters could go in the first slot. The second slot, you then would have only 4 letters left that could go in there because one of the letters has been chosen. Now there's only 4 left for the second spot. Then there's only 3, 2, 1, giving me a total of 5 factorial different ways in which I could sort those numbers. The reason it's 5 factorial is because 5 factorial means 5 times every number less than 5. So it'd be 5 times 4 times 3 times 2 times 1. If you throw that in your calculator, I believe the answer is 120. That doesn't seem right. Oh, it is right, 120. Ha! How lucky is that? So that is what we did yesterday. It's called the fundamental counting principle. It's how you figure out the number of combinations that you could do of something, or the number of arrangements. It does get harder. It gets harder because they'll start to add rules. The first type of rule that we have is called a restriction rule. That's where they give you something that you have to do. So for instance, this one says, what if the letter M must be the first letter? They've given us a rule. M must be first. We're still going to use our fundamental counting principles. So we're going to say, okay, there's 5 options here. But now we're going to change the numbers that go in each slot. The way we handle rules is by placing the rules first. The rule said that M must go first. That means the number of different letters that could go in the first spot is 1. There's only one option. It has to be the letter M. There's no other choices. Once you've placed the rule, you then place the rest of the letters. In the second spot, I now have 4 options, right? I could put the letter P, letter R, the letter I, or the letter E into that second spot. But I could not put the letter M because I've already used the letter M. Then in the third spot, there would be 3, then 2, then 1. This is 1 times 4 times 3 times 2 times 1. If you put that in your calculator, you will get 4 times 3 times 2 times 1. You get 24 different ways that you could sort the letters in the word prime where the letter M goes first. Cool. Part C has a couple rules. So it says, what if the letter R must be the third letter and P or E as the first and last letters? All right, we're still going to do fundamental counting principle. There's 5 total slots that we can put these letters. And then we're going to start to sort the rules. The first rule is that R must be the third letter. All right, that means you go to the third spot, which is this spot, and you say there's only one choice to go there. It has to be the letter R. Then you're going to go to the next rule. It says P or E must be the first and last letters. So if you go to the first spot, you have how many options of letters to put there? You have 2. You could put the letter P or the letter E. You don't know which one you're putting there, but you have 2 options. Once you've chosen one of those letters, you now only have 1 option for the last letter. Sometimes people put 2 and 2, which isn't correct. It's 2 choices for the first spot, 1 choice for the last spot because one of the letters is now gone from P or E. You then have these 2 remaining spots. The only letters that could go in those remaining spots are M and I. So in that first blank spot, I have two options. I could pick either of the two remaining things. And in this spot, there's only one choice. It's whatever's left over. These numbers, again, remember, in fundamental counting principle, are all being multiplied together. So 2 times 2 times 1 times 1 times 1 equals 4. There's 4 options or 4 ways in which you could sort it so that R is the third letter and P or E are the first and last letters. Awesome. That's dealing with restrictions. Always place the rule or the restriction first and then do everything else. Let's try another one. This is a different type of restriction. We'll start off basic again. So it says Jimmy's arranging the letters in the word brain. How many ways can he arrange the letters? Well, there's 5 letters here. 1, 2, 3, 4, 5. That means in the first spot, he has 5 choices, then 4, then 3, then 2, then 1. Since there's no rules or anything, I just get to put those numbers and multiply them together to get a nice, cool 120 ways that I could sort the letters in the word brain. Part B. How many ways can he arrange the letters if the vowels must be together in the order AI? Okay, this is called a grouping question. The way we tackle grouping questions is we treat the group as one thing. So for instance, the letter B in brain is one thing. The letter R in brain is one thing. The letter N in brain is one thing. And then the letter AI, I am now treating as just one thing. It has to move together, and it has to be in the order AI. This means that now when I do my fundamental counting principle, I don't have 5 letters. I have 4 things that I can move around. I have the B, the R, the N, and the vowels. In the first spot, that means there's now only 4 options. In the second spot, there's 3, then 2, then 1. If you multiply those all together, that tells you that you have a total of 24 different ways that you could sort the letters in the word brain where A and I are together in the order AI. That is how we tackle grouping questions. We treat them as one thing. Now, part C is very similar. The difference in part C is that in part A, they said in the order AI. That's important. Part C does not say that. So we're still going to do the question pretty much the same way. We're going to say there's the letter B, the letter R, the letter N, and then the vowels. And we're still going to treat them as one thing. So that means we're still going to have 4 times 3 times 2 times 1 ways that we could sort these letters to say that there's 24 different ways in which I could arrange B, R, N, and the vowels AI. But then there's another part to this question. The second part to this question is dealing with this. You now have to ask yourself, how many ways could I rearrange those letters? In that group, there's 2 things, the letter A and the letter I. In the first spot, I have 2 options. I could put A or I. In the second spot, I'll put the other letter, meaning that there is 2 ways in which I could sort A and I. Now you have 2 numbers. This number 24 is sorting the main group. This number 2 is sorting the subgroup. So it's like the little group, the AI. To get your answer, you then multiply the 2 groups together because you want to sort the main group and sort the subgroup. giving me a total of 48 combinations in which I could sort the letters in brain where A and I are together in any order. Fantastic. Let's see how this question could work without letters, and we're talking about people. So this question says 4 adults and 5 children go to watch a movie. How many ways can they sit together? Okay, well, we have 4 adults and 5 children. That is a total of 9 people. We're asking how many ways could they sit at a movie theater? Well, there's 9 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. In the first seat of the movie theater, any of those 9 people could sit down. In the second spot, any of the 8, 7, 6, 5, 4, 3, 2, 1. That is the same thing as saying 9 factorial. If you calculate it, got the hiccups going right now. 9 factorial, or 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1, is 362,880 ways in which those kids and parents, or sorry, I don't know if they're parents, those 9 people could sit. Awesome. Part B. How many ways can they sit together if the 5 children want to sit together? Perfect. This is like a grouping question, right? We're grouping those kids together. That means you now have to consider the adults as individuals. So there's 1 adult, a second adult, a third adult, and a 4th adult. Then you have 5 children. 1, 2, 3, 4, 5. And they move as one. You treat them as like a package deal. This means that there's now only 5 things that you are sorting. The 4 adults and the children. To calculate this, I would go 5 times 4 times 3 times 2 times 1. That would equal 120 ways in which you could sort the 4 adults and the children are all together. I call this, that looks like a 3. I call this sorting the main group. That's considering everyone together. But we never said the order in which the kids sit, right? We've just grouped them all together. We have to remember that these 5 kids, they could then rearrange themselves and sit however they want. So we have to redo it again for the smaller group of kids. We go 5 times 4 times 3 times 2 times 1. That's another 120 ways that you could sort the kids. I call it sorting the subgroup. To get your final answer, you multiply the 2 groups together. 120 times 120 would give you a total number of 14,400 ways in which the kids could all sit together. Awesome. Part C. How many ways can they sit together if the children are all together and the adults are all together? So they went out to a movie and the kids are like, we all want to be together. And the adults are like, well, we all want to be together too. We don't want to be near you kids. Now, we want to sort the main group, but it's going to look like this. We have all the adults, 1, 2, 3, 4, and I treat them as one group. Then I have all the children, and there's 5 of them, so 1, 2, 3, 4, 5, and I treat them as one group. I still have 2 things I need to sort. I have all the children and all the adults. That means there's 2 spots, 2 times 1. That's me choosing whether the adults sit first or the children sit first, and then who sits second. I call that sorting the main group. That's everything together. Once the main group is sorted, I then have to sort the adults, which is one subgroup, and the children, which is another subgroup. So we'll do the adults first. There's 4 adults. That means there's 4 spots they could sit. Any of the adults could sit in the first spot, then another adult, then another adult, then another adult. 4 times 3 times 2 is 24 ways. I call that sorting a subgroup. In this case, that's me sorting just the adults. I then have to do it again for my other subgroup, which in this case is the children. Oh man, my computer is lagging. This gets frustrating. There's 5 children, so there's 5 spots. Any of the 5 could sit there, then 4, then 3, then 2, then 1, giving me a total of 120 ways that you could sort the children. Now that you have 3 numbers, you're still going to multiply them all together. You sort the main group, and you sort the adults, and you sort the children. Notice that I'm saying the word and then writing a multiplication symbol. That's a reminder that and means to multiply. So if we put that in our calculator, that gives me 5,760 ways that I could sort the adult all together and the children all together. I call those grouping restriction questions. They happen all the time, typically with people sitting together. All right. A game. Hurrah. Remember with these games, they're meant to take a significant amount of time. So I want you to try this game, try to read the rules, and then try to complete the game. I'll pause the video. You pause the video as well, and then try your best. Okay. Hopefully you attempted this game. The trick is to always read and figure what the rules are so you know what the heck the game is. So reading this, it says, the intention of a particular 2-player game is to create a line of 4 adjacent squares using the same letter. The word adjacent means in a row. It could be diagonal or front, back, side, doesn't matter. To play, each player takes turns placing their first initial somewhere on the 6x6 grid. Margaret and Gerda have started playing this game as shown on the grid below. Okay, you can see they've started. They've started putting their letters down, right? They're trying to get 4 in a row. The question says, it's Margaret's turn, and she determines she can guarantee a win by placing letter M in row what, column what. All right, so they're saying she's won the game. Where can she place the letter M to guarantee she wins? Sometimes when people do this question, they try to look at this grid and they try to figure out where she can put it to win right now. The number one mistake I see is that people think she could put an M here. Apparently I can't draw M's. And people say, well, that's 4 in a row. 1, 2, 3, 4. Adjacent means you can't have a bend in your curve, right? So that would not work. In fact, Margaret can't win the game on her current turn, but it says she can guarantee to win the game. That means she could create a situation where she'll win in her next turn after that. The way that she's going to do that is by putting an M right here. By putting an M in that spot, she creates 2 situations where she'll win. That's one situation if she puts an M there, and that's a second situation if she puts an M there. And because she's created 2 situations where she's going to win, Gerda can't possibly stop both ways in one turn. She could either stop the green line or the blue line, but she can't stop both. So by putting an M in that spot, she guarantees that she will win the game eventually. To answer this question, you would have to say that she needs to place the M in row 4 and column 2. So the answer should have been 4-2. I don't think there's any other answers to that question. I think that's the only spot you could possibly place the letter M so that Margaret is guaranteed a win. Cool. Hopefully you got that. If not, hopefully you at least persevered and put in a really good effort. Those questions are meant to take a long time. They budget you like 10 minutes. It's a lot of time to work on these brain teasers. Okay. Let's get into perms and comms. Perms and comms. What is a perm? What is a comm? So a permutation and a combination is a way of sorting things and figuring out the number of options. It's kind of like fundamental counting principle. So similar to what we were doing up here. It's just another strategy. What's the difference between them? Okay, well, let's talk about that. A combination is for when order does not matter. So if you're in a question and the order in which you pick things doesn't matter, that's called a combination. A permutation is a question in which order does matter. So permutation is for when order does matter. It's almost a guarantee you will get a question where you have to know the difference between perms and comms. You just have to know whether order matters or not. The way I like to remember which one's which. Everybody here has a locker combination. Well, actually, that's not true because we don't have lockers this year. But in the past, you've had a locker combination. Your locker combination should not have been called a locker combination. It should be called a locker permutation because the order in which you put the numbers into your lock matters. It's actually a locker permutation. It's named the wrong thing. And that always reminds me that permutation order matters, combination order doesn't matter. Some examples of things mattering and not mattering. We got 4 here. We're going to label them as perms or comms. So the first one says you're going to select 4 students from a group of 10 students to pick up garbage. Ask yourself, does the order in which you pick those students matter? The answer is no, it doesn't matter. If there's 10 of you in the room and I pick you first or I pick you fourth to clean up garbage, you don't care, right? Like either way, you're stuck picking up garbage. It doesn't matter if you're the first person picked or the third person picked. You all got stuck doing the same job. You all got stuck picking up garbage. Order does not matter. That is a combination. Question B, selecting 5 toppings out of 8 toppings for pizza. Okay, let's just simplify this a little bit. Let's pick 2 toppings. If you're picking toppings for a pizza and I call up Pizza Hut and I say, hey, I want a ham and bacon pizza. Does it matter if I say I want a ham and bacon pizza or if I say I want a bacon and ham pizza? It doesn't matter. Either way, when they make that pizza, they're going to put ham on it and they're going to put bacon on it. I'm never going to know the order in which they put those ingredients on. So this is a combination. The order does not matter in which you put those 5 toppings. Now, if you're a pizza person like me, it does matter. But technically, we're supposed to say it does not matter which order you put it in. C, selecting 2 teachers from H.J. Cody to be the new principal and vice principal. Okay, let's say that Miss Lambert and Mr. Garrow have left the school. We now need to pick a new principal and a new vice principal. You get 2 choices from H.J. Cody. The first person you pick will be principal. The second will be vice principal. So, does it matter the order in which you pick the teachers? If I pick Miss Round first and Mr. Hart second, I now have Miss Round as principal, Mr. Hart as vice principal. Is that different than if I pick them in the opposite order? If I pick Mr. Hart first, then Miss Round second, I now have Mr. Hart as principal, Miss Round as vice principal. That is different. This means that the order actually does matter in which you pick them, making this a permutation. When it comes to selecting people for like things to do, like if you look at A, we picked 4 people to pick up garbage, and C, we picked 2 people to be principal and vice principal. If there's a job given or a role, so getting picked makes a difference because you get a different role, then it's a permutation. If there's no roles and you're all doing the same job, it's a combination. Kind of a good rule of thumb. And you look at D, for instance, you are selecting a starting goalie and a starting captain from 11 students for a game of soccer. Notice that I'm giving them jobs, right? The first person will be the goalie. The second person will be the captain. That is giving them jobs. If you don't want to be goalie, you definitely don't want to be the first person picked. So this is a permutation because the order matters in which I'm picking them. I will guarantee you get a question on that. Whether you write the diploma exam or my exam, that will be tested. You will have to be able to know whether you have a perm or a com. All right. Let's try some perms and coms. Mr. Kennedy is making a 6-digit code for his iPhone and doesn't want to repeat any of the numbers. How many different codes could he make? All right, we're going to do this 2 different ways. We're going to do this using fundamental counting principle, like we did in previous questions. The reason I'm going to do that is because I'm making a 6-digit code. That means there's 6 spots. 1, 2, 3, 4, 5, 6. And my computer is lagging so badly that it's just drawing straight lines. And now it's moving the lines, even cooler. Oh, the frustrations of technology. I think one of the most frustrating things in the world is legitimately when technology does not work. It like makes my blood boil. So we have 6 digits, so we have 6 spots. 1, 2, 3, 4, 5, 6. There we go. Then I can say, all right, how many numbers could go in the first spot of my code? Well, the number of different numbers that could go in there is actually 10. Sometimes people put 9, but there's 10 different digits you could put there. You could put 1, 2, 3, 4, 5, 6, 7, 8, or 9, but you could also put the number 0, meaning that there's 10 options for that first spot. It then says that you don't want to repeat any numbers. So in the second spot, there's no longer 10 options. Now there's only 9 options. In the third spot, there's now only 8 options. And then 7, and then 6, and then 5. This is not 10 factorial because it doesn't go all the way down to 1. This is just 10 times 9 times 8 times 7. Oh boy. I'm about to lose it. 10 times 9 times 8 times 7 times 6 times 5. There we go. If you put that in your calculator, you will find that the total number of 6-digit combinations you could make is 151,200. That's the number of cell phone combinations you could make without repeating any digits. Perfect. That's the fundamental counting principle way. Honestly, that's the best way to do it. Technically, though, you could also do this question as a permutation because the order matters in which you do this question, right? If I have a password, the order matters in which I put it. So this is a permutation question, which means we're going to use the permutation formula. The permutation formula looks like this. I'm going to write it on the left side over here. It goes N, P stands for permutation, and then R. The N and the R represent numbers. The N represents the number of things you choose from, or the number of, let's say, options. I apologize for the writing. This computer is Struggling. I don't know how it's struggling. There's nothing else going on. I'm making this film late at night. There's no one on the internet. And yet here we are. So N is the number of options, and R is the number you pick. So for instance, for this question, there was 10 options because there's 10 different numbers to pick from. And I want to pick 6 of them. Right? There's 10 numbers to pick from. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to pick 6 of them for my password. You could put that in your calculator. You go 10 and then you hit math. Oh my goodness. You hit the math button. You then hit the right arrow 3 times so that you are underneath the category that says P, R, B. And you will see that the second option is NPR. Depending on your calculator, you will actually be able to write the numbers as small little numbers. If you have an older calculator like me, it'll just say NPR on your screen. And you'll type 10 NPR and then type the number 6 and hit enter. If you do that, that means 10 permutate 6, and it equals 151,200. Like that. I do want to stress that permutations and combinations can only work for questions where you can't repeat things. If I had repeated numbers, permutations doesn't work. All right, let's look at a couple of questions here, and let's try to use permutations instead of our fundamental counting principle. So this says, how many ways can the letters from the word frankly be arranged if all the letters are used? All right. The order matters in which I put these letters because it makes a different word if I put different letters in different order, right? So this is a permutation question because the order matters. The first number is the number of things I'm choosing from, the number of options available. For this question, there's 1, 2, 3, 4, 5, 6, 7 letters in frankly. So the first number would be 7 because there's 7 numbers I get to permutate. And I'm using all the letters. So it would be 7 permutate 7. If you put that in your calculator, you will get 5,040. That means there's 5,040 ways that you could sort the letters in the word frankly. For part B, they change it up a little bit. It says, how many ways can the letters from the word frankly be arranged if only 4 letters are used? So now it's still a permutation question, and I still have 7 letters I can choose from. But instead of sorting all 7, now I'm only going to sort 4 of them. So I might go FANL, right? Only 4 letters are being chosen to make a word. This would be 7 permutate 4. If you put this in your calculator, it is equal to 840. Holy Moses. You ever heard your teacher have a meltdown on a YouTube video? Because we're getting pretty close to that moment. 840. Holy. There we go. 840. Whew, took a while to make it, but we got there. If you wanted to imagine doing that question without permutations, you could do it using fundamental counting principle. This time, there would only be 4 slots, though, because you're making a 4-letter word, right? And then in that first spot is not a 4. In that first spot would be a 7 because there's 7 different letters in Frankly that I could choose from to go in that first spot. In the second spot would be a 6 because one of the letters is gone, and then it's 5, and then it's 4. If you multiply that all together, you get 840. So same answer, different strategy. Part C. If the letter A must be the first letter and all letters are used. Oh, okay. This changes things a little bit. This is now a fundamental counting principle with a rule. A must be first. So I would definitely do this as a fundamental counting principle question. There's 7 slots. Because A must go first, that means there's only one option in the first spot. Then I can do the rest of the question. In the second spot, there's now 6 letters left over, then 5, then 4, then 3, then 2, then 1, giving me my mathematical equation, 1 times 6 times 5 times 4 times 3 times 2 times 1. You put that in your calculator, it's 720. That's 720. Whoa. Wonderful. At least at most. I think we're going to stop there because I don't think I can handle this lagging computer, and I'm worried that it's going to crash and I'm going to lose everything. So that's good. Oh, we're almost at half an hour anyway. So that's good for today. We will pick up tomorrow with some more at least at most questions. We'll also mix in some probability questions, and it'll be a lot of fun. You'll love it. All right, take care. I'll see you all soon.